Okay guys, what's up? Welcome back to linear algebra. Today we're talking about bases. So, last time we talked about span and linear independence. Here's the idea. Span told us how to make subspaces from lists of vectors, and linear independence tells us when the span doesn't have any extraneous info. That is, here's kind of the idea. You can take a bunch of vectors and you can make a subspace from them. Sometimes you can take two different lists of vectors and make the same subspace. If one list is shorter than the other, it sort of says that the longer list has information that wasn't really even necessary to specify. So linear independence tells us when our list is so compact that removing anything would genuinely get rid of information. Okay, cool. We're going to put these two things together to define a basis. So a basis of a vector space V, it's just a list of vectors. That's important since lists are ordered. So it's a ordered collection of vectors that is linearly independent and spans the entire vector space. Here's kind of an example. You guys have definitely seen this before if you've taken a first linear algebra course, which I'm assuming everyone has. Let's take like V1 to be 0, 1, and let's take a V2 to be, I don't know, 2, 0. How about something like this? Then, if V is equal to some xy in R2, let's say, let's notice that A1 V1 plus A2 V2 is equal to, well, what are we going to get? A1 V1 will give us 0 A1 plus A2 V2 will give us 2 A2 0. And if we put this together, we get 2 A2 A1. Okay. And V equals A1 V1 plus A2 V2 has the unique solution. Well, all we have to do is set A2 equal to x over 2 and A1 equal to y. Okay. Cool. So, notice, what does this tell us? Well, every vector v in R2 can be written as a linear combination of v1 and v2, and it can be done, and this can be done in only one way. So, v1, v2 is a basis of R2. Notice, under our convention, v2, v1 is a different basis of R2, since bases are ordered. Okay, cool. Let's prove some results about bases. Here's the first one, the criterion for a basis. So we've got a list of vectors in V. Let's suppose that it's a basis. All right, then every V in V can be written uniquely as a linear combination of these guys for some scalars in the field. Conversely, if every V in V can be written uniquely in this form, then this guy's a basis. That is, let's justify this example I just did right there. So here is the idea. So in the forward direction, let's suppose that V1 through Vn is a basis of V. Okay. Let's let V be a vector in V. So since V1 through Vn spans V, it follows that there are scalars A1 through An in the field such that V is equal to A1 V1 plus dot 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 all the way up to An Vn. All right, cool. That's just from the definition of span. Nothing too crazy right there. Now, suppose, I'll just use the quick suppose, that C1 through Cn, oh, I'm lagging out, what the heck? Cn in the field also satisfy V equals C1 V1 all the way up to Cn Vn. Then, watch this. Why am I lagging out? 0 is equal to, well, V minus V, which is certainly equal to A1 V1 plus dot, 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 all the way down to AN Vn, okay, minus C1 V1 plus dot, 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 all the way down to Cn Vn. Okay, nothing too crazy so far. And if I do a little bit of reorganizing right here, I can just get A1 minus C1 V1 plus dot, 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 all the way down to AN minus Cn Vn. Okay, nothing too crazy. Nothing too crazy so far. We're just using some properties that we've already proven are okay, and as well as some like assumptions from V being a vector space. That is, that addition is commutative, that scaling distributes over addition, and we're also implicitly using the small fact right here that the additive inverse of a vector is minus the additive identity of the field scaling the vector. So we're using that little piece right there too implicitly, so we can break everything up and reorganize terms like this. Okay. But since a basis is a linearly independent set that spans V, this means that AI minus CI equals 0 for I equals 1 all the way down to M. This follows from a result we proved last time, which said that if the only way to write the 0 vector as a linear combinations of the vector v1 through vn is with the coefficients all equal to 0, then the set v1 through vn, the list of vectors, is linearly independent. Okay, cool. So this tells us that these guys are all equal to 0. That is AI equals to CI. Oh, this told us that, hey, look, there is a unique way to write every vector as a linear combination of v1 through vn. That is, if you chose some other c's, oh look, they actually were the same. You couldn't choose other ones. You could only choose these ones. All right, nice. Now, in the reverse, suppose that v equals a1 v1 plus 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 dot 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 through an vn has a unique solution a1 through an in the field for all v in v. Okay. This certainly implies v1 through vn spans v, since it says every v in v is a linear combo of v1 through vn. Now, to get uniqueness, so to get linear independence, all we have to do is this. For linear independence, notice that this implies, in particular, that the solution a1 equals dot 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 all the way down to equals an equals 0 to 0 equals a1 v1 plus dot 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 an vn is unique. So v1 through vn is also linearly independent. Hence, it is a basis. Nice. Okay, cool. So in the reverse direction, we just go, hey, look, if this has a unique solution for every v, then certainly every v is a linear combination of v1 through vn. So the list of vectors v1 through vn certainly spans v. Now, by the uniqueness of that, the uniqueness of the coefficients that give any vector as a linear combination of v1 through vn, just the fact that you could take all of the a's as 0 to get 0 tells us that's the only way you can do it. That is, if it's unique, then having one solution tells you that that is the only one. But having this equation have only one solution given by this tells us that the list of vectors v1 through vn is linearly independent. We proved that at the end of class last time. All right, so it's a basis. It's a linearly independent spanning set. Nice, or spanning list. Cool. So let's see what else we can do. Okay, up next, we're going to show that every spanning list in a vector space can be reduced to a basis of the vector space. So let's start by, let's let v1 through vn be a spanning list for v, i.e. the span of v1 through vn equals v. Remember, a list, we're always assuming, is finite. So automatically, we're getting that v is spanned by a finite list, hence is finite dimensional. Though we haven't defined dimension yet, this just means that there is a finite spanning list. Okay, so let's take a spanning list. So here's the idea. Step 1. If v1 is equal to 0, delete v1. If not, do nothing. Okay. Now, I'll write this as step k. Here's the idea. If vk is in the span of v1 all the way up through vk minus 1, delete vk. If not, do nothing. Okay. This process eventually stops. Why? This is a big important piece right here. Why does this process stop? Either we discard nothing and have only the list v1 through vn, which spans v, or we have some new list, I'll call it w1 through wn, m, how about, with wi in v1 through vn, and indeed in order, right? So that says with I will write it as this with if wi is equal to vj, then wt is in v1 up through vj for t less than I. That is, it's still in order. Still in order, just missing a few. So we either get the original list or some new list that is the same except for we've cut a few of them out. And by the linear independence, or not independence, linear dependence, the linear dependence lemma, this list is independent. Since if it were dependent, we could choose some, I'll write it as WK, such that WK is in the span of W1 up through WK minus 1, and by construction, this is not the case. That is, every time, if we had something that was in the span of the previous elements, we got rid of it. So, this never happens. Hence, we are done. That is, we can take any spanning list and delete some stuff and get a linearly independent spanning list. That is a basis. Nice. Why does it still span? Well, because every time we delete something that's in the span of the previous things, we don't lose anything in terms of what we eventually span. That is, if the span of v1 through vk minus 1 is the same as the span of v1 through vk, then getting rid of vk doesn't remove anything from the span, and we're still fine. As we go, eventually we'll get up to the entire vector space since we have a spanning list to start with. All right, cool. Let's see what else we can do. Okay, so we showed that every spanning list contains a basis. That is, can be reduced to a basis. You can delete some stuff, keeping everything in order, and still get a basis. This has a nice corollary. So every finite dimensional vector space has a basis. If V is finite dimensional, it has a spanning list, which necessarily is only finitely long, of vectors. By the previous, this can be reduced to a basis. So we're done. Easy. All right. Can we do anything more like this? I claim, yeah. Every linearly independent list extends to a basis. That's kind of cool. So you can take a spanning list and you can reduce it to a basis, and you can take a linearly independent list and add a few more things and make it into a basis, not shuffling the order of the original things in any way. So let's let U1 through UM be a linearly independent list of vectors in V, which we'll assume is a finite dimensional vector space. Okay, so if V is a finite dimensional vector space, there exists a spanning list for V. Call it, let's say, W1 through Wn. Form the list U1 through UM, W1 through Wn. This certainly spans V, since it contains a spanning list. This certainly spans V and can be reduced to a basis using the process from the result, or I'll say instead of the result, from the proof of the result before last. That is the one that we did just before this one up here. Okay, so this can be reduced to a basis. Okay. This process deletes none of the UI, since UI is not in the span of U1 through UI minus 1 for any I in 1 through M, as U1 through UM is linearly independent. Hence, the obtained basis starts with, I'll put that in quotes, but you understand what I mean. It's a list. So the beginning of it starts with the UIs. So we are done. That is, we take this new list, which you take your linearly independent list, you take any old spanning list and you just pop it on the end. Then, since this big thing here is a spanning list and hence can be reduced to a basis, we can pop a few of these guys out and get a basis. None of the things we get rid of will be the U's, since none of the U's lie in the span of the things before it in the list, which are also U's. This just follows from linear independence. So every time we remove stuff, it's from the W's. All right. And once we're done removing things, we have a basis. We've only removed W's. The basis still starts with U1 through UM. We've extended the list U1 through UM to a basis. Oh, sweet. Let's do a little bit more. All right, last up, we have this result. So let's suppose that V is finite dimensional and U is a subspace of V. What we're going to show is that there is a subspace W such that V is the direct sum of U and W. So for every finite dimensional vector space, in every subspace, there is like a complementing subspace, if you want to think of it that way, another piece of V, such that you can form V as the direct sum of the subspace you started with and this other complementary piece. All right, let's put it together and let's see what we can do. And I'll give you some intuition for why this is a nice result at the very end and sort of put it all together. So to start off with, let's suppose that V is finite dimensional. Let's let U be a subspace of V. Then U is also finite dimensional. We proved this before. We proved that every subspace of a finite dimensional vector space is finite dimensional. Hence, there is a basis, let's call it U1 through UM of U. That is, we just showed that every finite dimensional vector space has a basis. Nice. This is because we can take a spanning list, which exists for any finite dimensional vector space, and reduce it to a basis using the process we described before. All right, so there's a basis of U. Now, okay, here's the thing to notice. Notice that U1 through UM is linearly independent in V, since it is in U as well. So a basis is a linearly independent spanning list. This is a linearly independent list of vectors in U. And since U is a subspace of V, it is a linearly independent list of vectors in V. Okay. So we can extend it to a basis. Let's write it as U1 through UM, W1 through WN, of v. This just comes from our last result, the one we just proved. This follows from the previous result. That is, you can take any linearly independent list, extend it to a basis, add some more stuff, make it into a basis. All right. Let's let W be equal to the span of W1 through Wn. Then, since I'll write it like this. Here, let me just even do, no, I won't here. U1 through UM, W1 through WN. I hate rewriting something like that, but since this is a basis for V, every little v in big V can be written as V equals A1, not V1, U1 plus dot 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 all the way up to AM, UM plus B1, W1 plus dot 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 all the way up to BN, WN for some A1 through AM, B1 through BN in the field. Okay, that is, there is some linear combination of U1 through UM and W1 through WN that gives you every vector in the space. Okay, nice. To get directness, recall that we need only show that V is equal to U plus W and U intersect W is equal to the 0 vector. So, to show that V is the direct sum of U and W, first we need to show that V is the sum of U and W, and then we need to show that U and W only intersect at 0. Since A1, U1 plus dot 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 all the way down to AM, UM is in U for any A1 through AM in the field, and B1, W1 through BN, WN is in W for any B1 through BN in the field. The fact here, this guy, tells us we can write any V in V as V equals U plus W for some little u in big U and little w in big W. Hence, V is equal to the sum of U and W, those two subspaces. Now, since U1 through UM, W1 through WN is a basis, it is linearly independent. How are we going to use this? So, here's the idea. Okay. The only way to write 0 equals A1 U1 plus dot 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 AN AM UM plus B1 W1 plus dot 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 BN WN. Wow, a lot of writing right there. Is with A1 equals dot 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 all the way down to AM equals B1 equals dot 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 all the way down to BN equals 0. So, suppose that V is in the intersection of U and W. then V equals A1 U1 plus dot 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 all the way down to AM UM for some A1 through AM in the field, and V equals B1 W1 plus dot 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 all the way down to BN WN for some B1 through BN in the field. Hence, 0, that's V minus V, and that's equal to A1 U1 plus dot 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 all the way down to AM UM minus B1 W1 minus dot 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 all the way down to minus BN WN, and we get A1 equals dot 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 all the way down to AM equals minus B1 equals dot 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 all the way down to minus BN equals 0. And if V is equal to the linear combination A1 U1 plus dot 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 all the way down to AM UM, and all of the A's are 0, if V is equal to 0. So V is equal to the direct sum of U and W. That is, we've shown that V is equal to the sum of U and W, and the only wet thing that lives in their intersection is 0. Hey, nice. All right, that was kind of a long proof, but this is a very good result. What this really tells us is that you can break down finite dimensional vector spaces in terms of any subspace. Start with any subspace, and you can break down V into a direct sum of that subspace and something else. And the way we do this is using bases. That is, linearly independent spanning sets. So the gist of it is that we take some set that spans U, a linearly independent spanning set for U. That set is just linearly independent in V, not spanning, but we can extend it to a set that is linearly independent and spanning. The additional stuff we add, that piece, that spans another subspace, and it does so in a way that is very nice with respect to V. That is, it spans a subspace such that V is the direct sum of the subspace we started and the span of those additional things we added. Very cool. We'll use this a lot, and we'll get a lot of mileage out of it. But for now, let's call it quits. Have a great day.